Okay, today we're going to do section 4.2 on the binomial distribution. The objectives for today is to determine if a probability experiment is a binomial experiment, to find the binomial probabilities using the binomial probability formula, and also using technology, so our calculator, so have your 84 ready, and a binomial probability table, and we'll need our book for that one. Then we're going to graph a binomial distribution and find the mean, variance, and standard deviation of a binomial probability distribution. A binomial experiment is an experiment that satisfies these four conditions. The experiment is repeated for a fixed number of trials where each trial is independent of the other trials, and there are only two possible outcomes for each trial. It can either be success or failure, and the probability of a success is the same for each trial, and the random variable x counts for the number of successful trials. Sorry, it got cut off. So we have notation for a binomial experiment. N is going to be the number of times the trial is repeated. So if you're going to roll a die 50 times, your N would be 50. P would be the probability of success of a single trial. So, and then Q would be probability of a failure. And P plus Q equals 1. So if you know what P is, you can find Q by subtracting it from 1. Because either it's success or failure, so the two things are the only possible outcomes. X is going to be our random variable, and it's going to represent the count of the number of N trials. So we can explain all of those through an example. So here, for our example of binomial experiments, we're going to decide whether the experiment is a binomial experiment. If it is, we're going to specify our N, our P, our Q, and list the possible values for each random variable X. We're going to go through what all those meant. So a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So this is an example of a binomial experiment. Each surgery represents a trial. There are 8 surgeries, and each one is independent of the others. So that fulfills one criteria. 2, there are only 2 possible outcomes of interest for each surgery. Either the surgery is a success or it's a failure. That's criteria 2. Criteria 3, the probability of a success is 0.85 for each surgery. The probability is the same for all of them. And the random variable x counts the number of successful surgeries. So if he had 8 surgeries, he could have 0 surgeries that were successful or 1 surgery that was successful, all the way up to 8 successful surgeries. So the random variable x would be the numbers 0 through 8, those whole numbers that I listed. So 8 is our N, it's the number of trials. P is the probability of success, which is 0.85, because there's an 85% chance of success. Q is the probability of failure, so the probability of failure is 0.15 or 15%, because 85% of the time it is successful, 15% of the time it's a failure. And 0 through 8 are the number of possible successful surgeries. Here's another example. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. So that means I'm going to pull a marble out, check its color, keep it out. Now I have 1 less marble in the jar, so I'm going to take another one out, look at it, keep it out, and then I'm going to pull the third one. So each time I pull a marble out, there's 1 less marble in there. So for this one, the solution, it's not a binomial experiment because the probability of selecting a red marble the first time was 5 out of 20 because there were 5 red marbles out of 20 total. Because the marble is not replaced, the probability for the second one to be red is no longer 5 out of 20 because there's only a possibility of 4 red out of 19 total that are left in there. So since the trials are not independent and the probability is not the same for each trial, this makes it so that it is not a binomial experiment. So if you do know something that is binomial, that fulfills those criteria that we went through, you can find the probability. So the probability of x, so it's exactly x successes and n trials, so it'd be NCX. So this would be our choosing formula from chapter 3. So n trials and x is the number of successes. P, so P was the probability of success, and x is the number of successes. Q is the probability of failure, and it's n minus x, because if you had x successes and you had n trials, n minus x would be the number of failures. From chapter 3, we knew that ncx, we used r last chapter, but it's n factorial over n minus x factorial over x factorial. This was just the definition of ncx. The remainder is the same. So here's an example. So the microfracture knee surgery has a 75% chance of success on patients with degenerative knees. The surgery is performed on 3 patients, and we're going to find the probability of the surgery being successful on exactly 2 patients. So method 1 is we're going to draw a tree diagram and use the multiplication rule. So the first surgery can either be a success or failure, and the second surgery can be a success or failure. So we could have a success and a success, or success and the failure, and so on. And then the third surgery could be success or failure for each of those. So the possible outcomes would be success, 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 failure, success, failure, success, and so on down the road. So we could list all of our possible outcomes. SSS would be success, 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 or success, success, failure, and so on. So I've highlighted all of the ones that have 1 failure, which means 2 successes. So the number of successes being exactly 2, there's 3 possible outcomes out of all of our outcomes that have 2 successes and 1 failure. So we can calculate the probabilities for each of those. The probability of 1 success is 0.75. So if it's a success and a success and a success, it's 3/4, 3/4, 3/4. Multiply those. Oops, excuse me. Or if it's success, success, failure, there's a 3/4 chance of success, 3/4 chance of success, 1/4 chance of failure. Since I want all 3 of those to occur, so the first one is a success, and the second one is a success, and the third one is a failure. Since it's and, we're multiplying. So if we wanted to find the probability of exactly 2 successful surgeries, I can see that it's 9 over 64, 9 over 64, and 9 out of 64, or 3 times 9 over 64, and this would be the probability of 3 successes. So that's method 1. Method 2 would be using the binomial formula, which is what we want to do. N is 3 because we're talking about 3 surgeries. The probability of success is 3/4. The probability of failure is 1/4. And x is 2 because I want to find the probability of exactly 2 successful surgeries. So plugging into our formula, we're going to use the fact that our n is 3 because there are 3 trials. X is the number of successful surgeries, which is 2. P is the probability of success, which is 3/4, and we're raising it to the x, which is 2 for 2 successful trials. Q is the probability of it being a failure, which was 1/4, and n minus x is going to be 3 minus 2, which is 1. So we're going to plug our 3c2 into our formula, 3 factorial over 3 minus 2 factorial all over 2 factorial, and we can just compute these, and you can use your calculator. I apologize, it did get cut off, but it says 3 times 9 over 16 times 1 over 4 equals 27 over 64, which is 0.422. And you can just plug this into your calculator. So a binomial probability distribution, for this, we're going to list the possible values of x with each corresponding to the probability of each. The binomial probability distribution for the microfracture knee surgery that we were doing, our n was 3 because we had 3 trials, and our p was 1/4. And we're going to use that to find the probabilities. So we have a probability distribution table here. On the previous example, we went through finding when our x was 2, what the probability was. So this is what we found. We would go through the same exercise to find the 0, the 1, and the 3 with those different x's and plug it into the formula. And that's how you get the probability distribution table. So for this example, in a survey, U.S. adults were asked to give a reason why they like texting on their cell phones. 7 adults participated in the survey, were randomly selected, and they're asked whether they like texting because it was quicker than calling. And we're going to create a binomial distribution for the number of adults who responded yes. So 56% like texting because it was quicker than calling. We talked to 7 adults at random, so n is 7. The probability of success in this example is 0.56. So subtract this number from 1 to get q, the probability of failure. And then for successes, it could be any number from 0 to 7 because we had 7 people. So we can find all of our probabilities by plugging into the formula. So when x equals 0, we're going to do 7 choose 0. And this is our p to the 0, q to the 7. So notice how you have a 7 here is the same as that 7, and the 0 is the same as that 0. So we're just going to be able to plug this line directly into your calculator. Please follow along so you can make sure you can get that. Then we do it for x equals 1. So when x equals 1, we plug in the formula, our n choose x times our p to the x times our q to the, now you do your 7 minus your 1. And all the way down, and you can find all of your probabilities. Please make sure you can do this on your calculator. Once you do that, you can list all of your x's and your p of x's that we found on the previous slide to construct a binomial distribution table. You can see that all of our p of x's are between 0 and 1, and if we added all of those numbers up, it would sum to be 1. So we know that it is a valid distribution. So the results of a recent survey is that 67% of U.S. adults considered air conditioning a necessity. If you randomly select 100 adults, what is the probability that exactly 75 adults consider air conditioning a necessity? And we're going to use technology to do this. So go ahead and get out your calculator. This is an example when n is 100. Our p is 0.67. That's having air conditioning. And so our q, we would subtract that from 1 to get our q, and our x is 75 because we want to know what is the probability that exactly 75 adults out of the 100 were selected feel that this air conditioning is a necessity. So this is the steps on your calculator, so please follow along. Please try this out and make sure you get this as your answer as 0.02, which means that you can see the probability exactly 75 adults consider air conditioning a necessity is going to be about 0.02. And that's how we use our calculator. The next one, we're going to use our table, and so here you're going to need your textbook. So here it says a survey indicates that 40% of women in the U.S. consider reading their favorite leisure time activity. You randomly select 4 women to ask them if reading is their favorite leisure time activity, and find the probability that at least 2 of them respond yes. Here our n is 4 because we're selecting 4 women. P is 0.4 because 40% of the women consider it their favorite activity, so Q, we subtract that from 1. We want to find at least 2 means 2 or more, and so we need to find the sums of probability of being 2 successful, 3 successful, and 4 successful. And we're going to use our tables to do this. So in our appendix, A8 is the page number in appendix B, we can find these tables. Since our n is 4, we're looking for n is 4, and then we have our x's 0, 1, 2, 3, 4. We're looking at x equals 2, 3, and 4 when our probability is 0.4. So we're looking at the probabilities 0.4 and the rows 2, 3, and 4. So we're going to look at these 3 numbers. So we have 0.346, 0.154, and 0.026. And those are the probability of 2 successes, 3 successes, and 4 successes. Since we want the probability at least 2, we're going to sum them all up and get a probability of about 0.526. So that's a little over 50%. Okay, please pause the video, read the problem. We're going to graph. Okay, you can see we selected 6, so n is 6. 60% own the video game console, so P is 0.6, and we're going to find the value of x for each. To find all of our probabilities, you could plug those values into the formula given. You can use a table when the probability is something that is on the table, or you can use your calculator to find each of those when x equals 0 through 6. And then you would graph x equals 0, it goes up to 0.04. 1 goes up to 0.037. And you would create your histogram where all of your bars touch. But from this point, you need to make sure that when you're given an x, you know how to plug that x into your probability formula for the binomial that was given. And also when you're given your x, plug this into your calculator using it. And sometimes it can work for the tables in the back of your book, but not always, because it didn't have all of the probabilities listed. It only had some of them. Okay, so this was graphing the probability distribution. We're going to continue on to the next video, which is mean and variance and standard deviation.